in-person events. It does go without saying that events like this are not possible without the support of our sponsors. So on behalf of the AtlanTec committee, I would like to sincerely thank all of this year's sponsors for their continued support. Throughout all the sessions today, we've heard from a number of speakers looking at how technology is being applied to solve sustainability and environmental challenges. Continuing on that theme, I'm delighted to welcome Conor McGann to AtlanTec 2022. A native of Dublin, Conor is joining us from San Francisco this morning, so I appreciate you being available to us early this morning, your time, Conor. So Conor currently leads the development of software and data systems at Plenty, an indoor vertical farming company with a mission to improve the health of people, planet, plants, indeed, and the planet. Conor brings over 30 years of industry and academic experience in the fields of robotics and AI to bear the challenge of sustainably growing delicious, nutritious, and pesticide-free fruits and vegetables at scale. Conor received his PhD in artificial intelligence from Trinity in Dublin in 1995 and has been a practitioner of AI in academia and business ever since, and has specialized in AI for autonomous robot control in the diverse fields of planetary exploration, ocean exploration, and personal indoor service robotics. In 2011, Conor founded Solariat, a Silicon Valley technology startup applying text analytics and machine learning to social customer care. Solariat was acquired in 2014 by Genesis, where Conor went on to found and led the AI product group. I first met Conor when I was interviewing for Genesis. I did not say no because I enjoy my time here. So thank you for that, Conor.
Joe wouldn't let me.
Joe wouldn't let you, yeah, exactly. No, thank you. So just before I hand over to Conor, a final reminder to keep your questions coming in during the talk. I'll be keeping an eye on the Q&A section. And with that, again, thank you, Conor, and I'll hand it over to you.
Great, thank you, Seamus, and hello, everybody. Lovely to meet you all or speak to you all from California. I'm going to now, hopefully you can see my slides, and I'm going to put it in presenter mode. Can you see that all right?
Not just yet, Conor.
You seeing that? How's that?
We've not got that coming up yet.
Let me try to share again.
Please.
Okay, let me just share. Okay. Boom. Okay, should see my screen.
See your screen now.
How's that?
Yes.
Okay.
Yeah, now we've got it in presentation mode. Perfect, Conor. Thanks.
Great. All right. Well, hello, everybody. Greetings to Galway. It's been a long time, 3 years or so since I've been there. I had a great time working with all the good folks in Genesis and socializing a lot in that wonderful town. So very fond memories. So today I'm going to be talking about AI and robotics and vertical farming. I've been at Plenty now about 3 years. I joined because the mission was very compelling, but also the problem domain is fascinating. So it's a very, so building a new type of farming system is a very challenging job. And today I'm going to be telling you a bit about what the problem domain is that we're working on, and why it matters. And then what it is we've built, the total integrated system, give you a sense of the full system that we built. And I'll go into a little bit more detail on the software and data side, which is really my realm. So the problem, farming has been around for humans for a very long time, about 10,000 years, starting in Mesopotamia. In the last, say, 150 years, it's gone through a huge transformation. With a whole bunch of technologies, tractors and irrigation systems, large outdoor fields, doing it at higher and higher scales, of course, fertilizers and pesticides, and genetic modification. And all of these technologies have produced enormous gains in productivity. But those gains in productivity have happened almost completely in the realm of calories, grains. So in a study done a few years ago, published by Harvard, they did an analysis of the recommended daily diet by food category. And they compared what people were actually consuming versus what the production capacity was per person. And you can see here, the red bar is what the production capacity is, and the I guess the olive bar is what the recommended daily average is. And if you look, for example, at sugars, as much as we may enjoy sugar, the recommended daily average is 0, and we produce way more sugar than we need. Dairy is almost properly balanced. We're slightly overproducing on dairy. But if you look at vegetables and fruits, you can see a huge imbalance. It's a factor of over 3 between what people are recommended to eat and what we are capable of producing. And you can see that whole grains we're overproducing. So the way our agriculture is applied is we're overproducing in certain areas and underproducing in other key areas that are vital to human health. Now, to solve this problem, we need to produce a lot more, and a lot more of the right kinds of things. And to do that, using conventional field-grown agriculture, we need a lot more land. The majority of fruits and vegetables are produced in a few very specialized climatic regions with a Mediterranean climate. As you can see them marked here, the Mediterranean basin, off the coast of California, where I'm living, central Chile, South Africa, and Australia, New Zealand, down on their coastal areas. And so these are very specialized climates that are ideal with the right soils and the right environment for producing fruits and vegetables. And the problem we have is that in order to bridge this nutrition gap for humanity at current population levels, we just need a lot more of this land. So here's an indication: 390 million hectares. That's about 57 times the total size of Ireland, or 10 times the size of California. And so that's a lot of very specialized land in a very prized areas of the world. And we just don't have that land available. Another problem that we have is, even if we did have this land, in many of the areas where we are producing fruits and vegetables, we have a growing water scarcity problem. So I live in California, and we're deep into a drought. We have wildfires here that are just awful, and we are already under drought restrictions, and it's only early spring, and this is just likely to get worse and worse with climate change. We've already massively depleted the aquifers in California, and so we're going to see more and more restrictions on the use of water, which makes growing fruits and vegetables on the land we have even more difficult and is impacting yields. Another problem that we see is the cost of weather events on food safety and yield. This slide documents a number of cases of pathogens, outbreaks of pathogens that have led to human health impacts and large recalls. And so 20% loss of direct bromine sales was a $130 million hit. That happened not too long ago out of California. And so food safety and weather events are costly and increasingly frequent. They just get worse with impacts of climate change. Another consideration, and if you're living in Ireland and you want fresh strawberries in the middle of winter, they can be hard to get. And the general problem of getting fresh produce from these restricted areas into local markets requires a lot of transportation. And so the number of food miles, this chart indicates sort of the transit paths of fruits and vegetables around the world with the global supply chain. And this takes a lot of carbon. It also takes time, which impacts shelf life and impacts the nutrition density in the plants when they finally arrive. It also drives crop selection. You find that a lot of crops grown in production agriculture are selected. Their genetics are selected for surviving the journey and showing up looking good, rather than for taste and nutritional quality. And so this is an impact of this global supply chain that we have, because we can't grow food local to markets all the time. So now that's the problem. The impacts are pretty substantial in terms of human health, where we have nutrition deficiencies. And the impacts are increasingly substantial in terms of land use. We cannot use more land. The land we have is under pressure. And we'd like a solution to be able to feed a growing planet properly so they can maintain health without devastating our environment further. Or in fact, better still, by reducing pressure on the environment. So what I'm going to do is I'm going to give you a quick video of one of our farms. This farm is in South San Francisco. It's a leafy green farm. And you can see it in action to get a sense of what we do. And then I'll talk a little bit about how it all works. So hopefully this will come through. Okay, so hopefully that all played fine. So that farm was our first generation production farm. It really was done at a market test scale in South San Francisco. The main grow area there is about the size of a basketball court. And then there's other grow components around that, but just to give you a sense of the scale of it. So there's a few things that you may have noticed in that video, and I'm just going to talk a little bit about some of them. So what you're looking at here is a propagation rack, and the way the life cycle of leafy greens goes from seeding to germination to propagation, and then we grow them out in a vertical plane environment. So when they're seeded into trays, and those trays are stacked on tables that are roughly the scale of a snooker table. And then these tables are loaded into germination chambers where they're maintained in a very, very nice, dark, damp, humid environment. And then once they germinate and they are ready to photosynthesize, we will move them robotically into these propagation racks. The scale of a propagation rack, it's roughly the size of a large 18-wheeler container. So maybe a 40 by 20. Our racks get bigger than that, but you can just think of that sort of scale. And they're multi-level. And so the way this system works is racks are put in on each different level, and they're put in one end and taken out the other end. So they're pushed through in a first in, first out flow, and inserted and removed with robots. And on their journey, some of the characteristics of grow spaces in general, you can see LED lighting. So Plenty has its own proprietary LED lighting that gives exactly the right wavelengths of light in exactly the right durations for the plants, so that they have their optimal growth and we're not wasting any photons. So and we can control lights at different parts of a grow space. So we can specialize the lighting treatments depending on what crops are in each area of the grow space. We also have these tables are flood and drain systems. So if you look down at the bottom one, you can kind of see that it has a certain depth to it. So we will have irrigation cycles that flow nutrient-enriched water into those bays and then drain them out over time. And we'll do that on a repeated basis to meet the nutrient and irrigation requirements of the plants. Again, this can be done on a per table basis, which means we can tailor things very much to whatever the plants need. I will also say that in this space, like all our spaces, it's richly instrumented with sensors. So we are measuring all important environmental parameters, and throughout the systems, we also have cameras as well that can be used to image the plants. This is a picture of a vertical grow room. And so the architecture of this system, what you're looking at here are towers. These towers are plastic, They are seated on both sides of the tower. The tower is roughly a 4x4, 4 inches by 4 inches around, and this tower is about 5 meters tall. Our next generation towers are about 8 meters tall. And we have several hundred plant sites per face per tower. These towers are on hooks on a conveyance system, and they are conveyed into this grow room on one end and out the other. Again, then they can be put in, entered and exited and handled using robots. These towers are too big for people to deal with, so it's robotically moved. And then within these grow rooms, we can control the relative spacing between the towers. So that in the early growth phases of the system, the towers can be densely packed. And as they mature through the grow line, we can spread them out more. And that way we make the maximum use of space, but we also give the ideal growing space for plants so they can reach their full size. You see also the lighting, and again, proprietary lighting to plenty. All grow lanes have their own lighting spines. And what might be hard to see, sort of these opaque plastic ducts also hanging, which give, that's our HVAC treatment. So we have a recirculating air system and a recirculating water system. All the water that is submitted into the system is recovered through drainage at the base of the towers, but also we recover it. The transpiration from the plants emits a lot of water, and that is also recovered by our HVAC system. So we have this is a recirculating hydroponic system. The irrigation is through nozzles at the top of the towers, at the top of each tower position, which will give irrigated water with the perfect amount of nutrient on a continuous or intermittent basis, depending on the plant needs. And we will only water the plants if the lights are on, so we don't burn them out. So this architecture allows us to grow at very, very high densities, and it allows us to maintain very good, effective control of the environment, taking advantage of the normal physics of gravity and the direction of heat rising to give good airflow and water flow. Here is a picture of one of our marquee robots. So going from the horizontal plane with seedlings matured into trays requires a lot of transplanting. This is a specially designed transplanter robot that we use, and it will pluck plugs from trays, and then it will plant them into towers. And then those towers are conveyed out. And using this kind of robot, pick up and lay down robot, it will pick up towers and hang them up on those hooks for conveyance into the grow rooms. And on the other end, it will remove those towers, unhook them, and lay them down for harvesting. Our harvesting is also a fully automatic process. This will just give you this cartoon will give you a little sense of the flow end to end. So as I mentioned, we have seeding, germination, propagation, transplanting, grow, harvest, pack, and ship. So these are the main material flow elements. The total cycle time for most of our leafy green crops, it's about 3 weeks, roughly, from seed to ship. We will harvest and ship on the same day, every day. So we have a continuous flow of fresh produce being shipped out to, it's same day delivery, basically. So they're close enough to be eaten by consumers on the day they're picked. No humans will touch these plants at any stage. The first human to touch them will be the consumer when they take them out of the clamshells. They don't need to be washed. This is a very clean room environment. You may have noticed from the pictures of the vertical grow room, those people looked like they were working in an Intel plant, but this is a clean room environment, basically. It's a very food safe environment, and there are rigorous food safety protocols followed. So we don't actually have to wash the plants at all. They're harvested, packed, and then they can go straight to the consumer without any need to wash. So we also have here, you might notice just a couple of things. The environment control is continuous for all material at rest. We must maintain precise environmental control of lighting, nutrients, HVAC systems. We also have to integrate sampling with labs. So throughout the system, there'll be samples taken on a regular basis, and we get those samples back from labs. And this is all data, and then we measure everything. So we're then monitoring all this data. We can make decisions on orchestrating the material flow based on what we find. And of course, we're controlling to achieve the target set points for all the environmental control. In the middle of all of this is what we call Plenty OS, which is the software and data infrastructure that is connected to all physical systems and all interfaces for users to interact with the system. It mediates all aspects of system behavior and orchestrates production to achieve production goals. And so that's what my team is responsible for. A couple of things just to highlight a little bit more about our growing platform. It's really defined by this, distinguished, I should say, by this vertical grow in towers. So in greenhouses, alternative methods, you have greenhouses, which is a single layer in an outdoor but enclosed environment. And they have limitations. There are still geographic limitations with greenhouses. You only have the one layer. And the precise control is much, much harder to achieve because you're having to deal with the variability of the environment. And so there are tools for covering these with screens, for opening and closing vents, but it's just more difficult to attain precise control. There are other vertical farms, indoor vertical farms like Plenty, but they all operate based on stacked horizontal planes. And so, you take those trays, you put them into smaller tables, and then you stack them on shelves. And the problem with those methods is you're only growing on one plane, and you're limited in your ability to achieve uniformity on those planes because they're smaller units. You don't have the same open spaces that we have in our vertical grow planes. And so in contrast, when we grow vertically, we have these, if you look at a picture of a Plenty farm, it looks like just a big wall of each grow lane, where we have open lanes for airflow across the whole thing. And we can achieve very, very precise control with this method. And we can grow on both sides of each grow plane. So we get much higher density. And there's nothing wasted as we go up, and we can go up higher and higher. And we're just getting incredible densities from a Plenty farm. So higher levels of control, better experience for the plants, and much greater density using our architecture. Just to summarize, with a Plenty approach, space productivity, energy photon productivity, because we have this large grow space that we can target all the photons at, with very little spacing in between, and with dynamic adjustment of spacing. So one thing I just want to highlight is when we start out, we have the towers very close together, and then they expand as the plant matures. In contrast with these stacked horizontal systems, they have to stay in the fixed positions that they're in, which means you're shining a lot of lights on a lot of empty space in order to achieve the ultimate spacing you want, or you're going to end up cramping the plants in their mature phase. This architecture is extremely modular, and we can apply it to multiple different crop types. We are growing strawberries, and I'll talk a little bit more about that. And we're testing this on many, many different types of crop. And the food safety of this process is really, really amazing, because water doesn't ever land on the plant surfaces itself. It's all an internal drip irrigation system, and it's all very carefully controlled, which gives us really, really tight control of the pathogens. So looking at all of this in totality, the automated farm that we've built, it's designed to give maximum flavor, maximum nutrition, maximum quality, and maximum yield. And that precise control gives a much better experience for the consumer. And because we don't wash them, you're getting everything on that plant. Nothing is destroyed when you wash it, which maintains much higher nutrient density. Also, to give you a sense of scale, if you think of one of our farms being the size of a soccer goal on a football pitch, that farm will produce the yield roughly of the full pitch. So we see yield gains of between 150 and 350 times that of field farming, which is pretty staggering. Pushing the limits of how vertical we can go, but those gains are incredible. And of course, this is an entirely closed system. You can do it anywhere. You can do it in the Arctic, in anywhere that you've got access to electricity and water, basically. So it's a very, very high potential technology for addressing the nutrition gap without consuming a lot of land. To talk a little bit more about the hygienic nature of this, this is a comparison of store-bought, triple-washed organic versus plenty never washed. And you can see different pathogens there in different colors. And on the left side, you can see, you know, in the coliforms, you can see mold and yeast. And on the right side, you can get a sense of the relative scale for plenty, thousands of times cleaner. And so without washing, we are thousands of times cleaner compared to a triple washed organic product. And that really gives us higher shelf life, higher nutrition density, and a much more food safe product. Switching gears now to talk a little bit about more the software system. If you think about the characteristics of a plenty farm, I think of it as it's a hybrid of two major classes of system. The first class of system is for dealing with the material at rest. And the material at rest is largely composed of vertical towers, LED lights, rich sensor suites, hydroponic water treatment, recirculating water, and a precision controlled environment. And this is really our grow space control problem. We also have material in motion, much like an intelligent manufacturing system. We have specialized automation equipment because towers, it's a very specialized thing to be able to manage a material flow process like this in our architecture. We have to deal with granular traceability. If anybody's worked in the the food industry, you know that you have to have very good traceability to be in compliance with regulations. So you can show exactly what happened and where it happened to whatever food is consumed by a consumer. So we need to be able to track precise movements of the plants to know which spaces they're in, and then link that to what happened in those spaces, so that we can trace all the way to finished goods what plants were where, which is really important for understanding final outcomes and tracking performance. But it's also important in the event of recalls, so we can figure out just exactly what products need to be recalled. With all this material in motion, and it's a large, our farms are large resources, and as I mentioned, there are very distinguished grow spaces within these resources, and so there's a lot of routing and orchestration of material into those systems. And then, of course, within those systems, depending on which zones plants are in, you then specialize the treatments of those plants to give the plants their optimum experience. And so that's a very potent orchestration system that's required. And then finally, you know, we do have humans, and they're not really running around fiddling with plants as indicated in that vertical grow picture. Mostly they're operating work centers, but we do have to interact humans and automation in a very collaborative way. Humans are required to do tasks that aren't automated, and they have to be queued up to do that. And then humans will direct some tasks for orchestration, or solve some problems that orchestration can't solve because of some mechanical difficulty, for example. And the last thing I'll say about all of this is, whilst you have material at rest and you have material in motion and you can track it all, what you want to do is compute the integrated plant experience. And I liken this to, for my friends and colleagues at Genesis, where we think about customer journey experience. Well, this is really thinking about the journey of a plant and tracking all the treatments that occurred to that plant and all the outcomes along the way allows you to develop very strong analytics, reporting capabilities, and tackle problems like optimization of experience. If I think of an AI-powered farm, this is a very abstracted picture of what you can think of as major components. So below, we have the farm with people, plants, and equipment. Farms can be commanded, and they can be commanded for directing robots, but they can also be commanded for sending set points to low-level control systems for environmental control. And then they're instrumented. We're tracking events from the robots. We're looking at interactions that users make, and we're also gathering data from thousands and thousands of sensors, cameras, and other kinds of sensors. And then what we do is we take in all that instrumentation, and then the job is to basically perceive the current state. So perception. This is a sort of standard thing in AI systems. You perceive your environment, you update your current state, you have some goals, and then you compute the right course of action to be able to achieve your goals optimally, hopefully. So the characteristics of an AI-powered farm: you need a perception capability, you will frequently need a prediction capability, orchestration is really that decisioning component, and then optimization allows you to make sure that you're making the perfect decisions, both in the short run, but also optimization for total capacity of the farm. And so there are all sorts of interesting operations research problems in allocating crops optimally through the farm and then orchestrating the flow of material through that. I'll talk a little bit more about perception. I won't go into much detail on it, but we in the area of plant science, they use a term called plant phenotyping, which many of you may be familiar with. What it really means is capturing the response of the plant to all its treatments. And so this is really a way of thinking about characterizing what the plant is experiencing and essentially what are the outcomes that we're seeing. And so cameras are an incredibly powerful mechanism for determining all sorts of interesting aspects of plants, measuring leaf morphology, estimating the canopy area, looking at plant density or plant and root quality, looking at total weight and biomass. And of course, these are all critical parameters for understanding quality, for looking for any possible defects in the plant. And so there are multiple applications of perception, both for control of flow of material, for prediction of final harvest yields, and for optimizing control inputs. So we invest heavily in perception. And this is not just on leafy greens, this is also in fruiting crops. This picture is taken, it's nothing we did, this is taken from the plant phenotyping organization. And there's a lot of people starting to pay a lot of attention to plant phenotyping, and it's growing over the past 10 years. Not surprisingly, with the growth in interest in indoor and controlled agriculture, automation, and with the explosion of capability in machine learning and computer vision. I will also note here that it's not just cameras. There are also powerful sensors for understanding plant response based on hyperspectral imaging, which is also a fascinating area. Looking at orchestration, the way we've broken out thinking about the farm is we've thought of discrete work centers, and these discrete work centers basically represent junction points in material flow. And so a seeding work center will seed tables and land them into a germ chamber. A propagation load work center will transfer from germ chambers into propagation racks. Propagation unload will move them into a transplanting system. Transplanting will take them out of trays and put them into grow lanes. Harvesting will take them out of grow lanes and then harvest them and then send them to a blending area. And the blending area is our packing center. And we have mixes of products, so we have to pull crops out, mix them together into tubs and ship into pallets and pack into pallets for shipping. And so there's a sort of obvious looking flow here, but there's a lot of routing that goes on and a lot of tracking that goes on to be able to execute tasks at this level. So we have an execution engine, which essentially has a daily task plan for each of these work centers. That task plan has to be carefully orchestrated. So for example, we have blends that will, say, blend 4 different crops. The blending order needs to be carefully optimized so that you minimize the amount of interim storage space. which means you have to determine the harvesting order of the towers, which means you have to determine the transplanting order of those towers, which means you have to determine the unload order from the prop racks, and you have to determine the seeding order in a table so that you can properly in the right towers. And it goes all the way back to seeding. So the optimum packing sequence ultimately determines the seeding order and placement in a table. And so you have to coordinate this material flow through the whole system. So we have a planning engine to help do that. And the execution engine then is a plan execution system, and it orchestrates people and low-level controllers in order to do that. To give you an example of this, what we want to do is raise the level of automation up to quite a high level so that humans are really monitoring and overseeing very, very large scale tasks and not very many of them. So there's minimum button pushing going on. So here's an example of a farm supervisor, and they want to seed 30 trays of arugula, load it into a table, and load that into GermStack 5. And that's a very simple concept for somebody to think about, but that actually touches multiple lines of a farm and orchestrates multiple different machines along the way. And so there's a seating area, there's a moving onto tables area, and table conveyance. All of that has to be done together. And so this high level task gets broken down into hundreds of lower level tasks that have to be coordinated. So this is very much a hierarchical control problem in order to be able to achieve the level of automation and control that we want for material flow. This is a very simple concept. It's called a Teleo Reactor. This is the sort of architecture we developed for underwater vehicle control in the 2008. But the principle is really very simple. You can just think of a control loop. So there's a controller, and it dispatches commands to a system, and it observes states from that system. And it can be receiving goals, and it can be generating observations. And if you think about this, it's basically the same pattern in a recursive structure. So one controller can control a system, which can in turn be another controller for another system. And so this very simple building block of a goal-directed feedback control loop is a very nice way to think about breaking up hierarchical control systems. And this was done on robots for indoor mobile manipulation and on an AUV. And it gives you a lot of flexibility for putting bounded contexts together for control and then assembling them to achieve higher and higher levels of behavior. Another little detail here is, I don't know if many of you are familiar with the actor model, but an actor is a computational entity that has very, very simple rules and capabilities. In response to a message it receives, it can send a finite number of messages to other actors, it can create a finite number of new actors, and it can designate the behavior to be used for the next message it receives. So react to a message, basically. And so this is a very simple thing. There is a open source system that is based on this paradigm called ACA, which I would recommend people explore. And what this allows us to have is stateful addressing of actors. So these actors can essentially mirror components of the farm and track different control loops at different stages of abstraction. They're asynchronous. They can be scheduled, so we can have it tick along at a certain rate to enforce a control loop. They have a very, very low footprint per actor, and this will scale out beautifully. So we can scale these out in a completely sharded, clustered environment, and it gives us a lot of resiliency. They can maintain their state, they can restore their state. You can have supervisors that will bring them back to life, and they can maintain goals across many iterations of a control loop and execute until they've achieved them. So this is the pattern that we've used because it so nicely mirrors a domain-driven design method for thinking about physical systems in the farm. And this has been working quite well for us. The last thing I will comment here, and for my colleagues at Genesis, they may have heard me rabbit on about these before, but behavior trees are a technique for orchestrating task execution. And they're very simple. It's a very simple hierarchical structure. You have nodes that can be ticked, and in response to a tick, it will execute, and it will either succeed, fail, or it will be running. And then you can just keep ticking this structure. And you have composition nodes and you have primitive nodes. The primitive nodes actually do work, and the composition nodes will enforce some logic of composition. So for example, at the top here, you see a sequence node, and you will tick the leftmost tree until the leftmost node until it succeeds, and then you will tick the middle node and so on. And you'll do that over and over again until you succeed all the way through. And I won't go into details on this. I would suggest, if you're interested, there's plenty of documentation online. But it was developed originally in AI gaming. It's really very simple. It's incredibly expressive. You can make it very simple. You can represent simple sequences. You can model decision trees with this. You can have hierarchical finite state machines. So it's really very simple. It's not intuitive for people to specify problems with this. So there's a learning curve to it, but it is proven very robust for working with real world physical systems. And so this is something that we have embraced, and it's proven to pair very well with actors that allow us to tick nodes like control loops on a schedule, which gives us the kind of hierarchical controllability that we're looking for. The last thing I'll say is planning. Talk about is planning. There's all kinds of levels of planning here. I'm not going to go into detail about it, but a planning problem is, given a goal state and given a current state, compute the set of actions to go from current state to goal state. Roughly stated, you can think of that as the planning problem. And those planning problems exist at multiple levels. So for example, one area where we have a very interesting planning problem is those propagation racks. We have a variant of our propagation racks in our new farm in Compton, LA, where it has lifts on both ends, and we can recirculate the tables through the racks. And this gives us much more flexibility on material flow and placement of tables. And what you end up with basically is a rack that has tables located all throughout that rack. And on any given day, you have to be able to get the tables out in an efficient order that are due for transplanting. So you basically have to defragment a propagation rack. And so that's an optimization problem that you can solve. And then you can orchestrate the farm to manage all the lift operations, to carousel those propagation racks, and to give you the tables out in perfect order and save you production time. Also, if you think about demand forecasts, very much like factory scheduling, but you've got demand forecasts, and then you've got a certain capacity in the farm. We have lots of constraints on what crops can grow where, and which ones can be grown with each other, how long they have to sit in place. And so there's a lot of constraints on resource allocation. And you end up with a complex optimization problem to solve, which is then used for determining optimum material flow during the day. So there's high-level planning to optimize total resource allocation, and then detailed task planning every single day to achieve the material flow that we want, so things come through in the right order. And then we execute according to that. So that's the AI stack, if you like, on top of which then we invest in perception capabilities and prediction capabilities that are more closely aligned with modern AI in the machine learning realm. Most of the planning algorithms that we use for orchestration are much more traditional symbolic AI techniques. I'll say a little bit about the business of Plenty. So I've been here 3 years. I think the company is about 10 years old. We've raised a lot of money. We've raised about $1 billion. This is a very expensive business to build. Couple of key things I'd like to point out. Walmart, probably most people have heard of Walmart. I don't think they're in Ireland, but it's the biggest retailer in the world. And they have partnered with us and invested in us to invest in this new category of fresh produce based on our technology platform. So we have a huge partner for a go-to-market, and they will be taking our produce from our new farm here in Compton when it comes online. I'll say a bit more about the new farm in Compton. I'm actually calling you all from a hotel room in Venice Beach, California. I'm about to go to our farm in Compton, LA. The farm I showed you initially was about 1/10 the size of the farm we're building in LA. LA is a bigger footprint with larger square footage. It's also a much taller farm. And it's a very, very high throughput system. And that will be a groundbreaking demonstration of capability of vertical farming coming online this year. The last thing I'll talk about is strawberries or berries. So mostly you saw in the video leafy greens in action. That was a leafy greens farm. That same tower architecture can be used to grow berries, and they're really good. And Driscoll's is one of the biggest berry providers in the world, and they too have partnered with us, both to develop optimum strawberry varieties, but also to go to market with a strawberry farm. And so that's a really exciting development for us as well. So as a company, you know, we're maturing the technology, we are getting it fit for scaling out, and we have very large global scale partners on both the leafy greens side and on the fruiting crop side to take these to market at scale. And with that, I will thank you all, and I'll be happy to take your questions.
Thanks so much, Conor. It's a fascinating project, and it's amazing to see how far it's come. You know, even in the 3 years that you've been there. I remember you talking to us about it just as you were leaving us here in Genesis, and it sounded really exciting. So it's amazing to see how far it's come in those 3 years. It's interesting to think about the different types of crops that you can grow, and you know, you talked a bit there about your investments in the berry side of things. Where does it stop, or where else can you go with this apart from your kind of your leafy greens and your berries? Have you thought about other types of crops that you might be able to grow, or is there a finite kind of set that you think you could service through that?
Well, we're not growing banana trees, you know, we're not, you know, so things
Or
with very
potatoes?
yeah, no, probably not potatoes either, like tubers, you know. So, you know, the characteristics of our architecture, obviously they have to grow in these pod structures within towers. But we can vary the pod sizes and the pod design, and then still link them together into vertical towers. And once you're in this vertical tower frame, everything else is the same. So the actual components of a tower can change to adjust for different crops, but then we can link them into this whole system based on that. So to answer your question, yes, fruiting crops, so tomatoes and strawberries would be first up, and various other kinds of berries. But we are also experimenting with other kinds of like peppers and things like that. So there's a pretty large addressable set of crop types that we can still add. Honestly, we'll be pretty focused on bringing product to market at scale with berries and leafy greens. That'll keep us going for a while. But we have a pretty substantial plant science research center in Laramie, Wyoming. And there they have all these pods that look basically the scale of a garden shed. And they've got loads of those running, and we've got all kinds of interesting trials going on there. So there's a large pipeline to research new crop types. But it's a pretty sophisticated process. It takes quite a while to bring a new crop to market, and because there's a lot of biology to do to figure out the right varietals that will grow optimally and how best to grow them.
Very good. I might get you to maybe unshare your screen there, just while
Sure.
we're going through the Q&A. A couple of questions coming in. So one from, I think it's Sean Edwards. Do you also develop, produce the nutrient water feed for the crops as part of your process?
The nutrient system. So we did spec out one of the earlier stage nutrient systems, and we obviously specify the nozzle structures and things like that, and the pumps. But generally speaking, we try to use off-the-shelf components as much as possible. So really, if you think about like, again, we don't manufacture our own conveyance systems either. We spec them out and use other vendors. The parts that are really, really proprietary to us are the tower architectures and specialized end effectors and integrated systems for transplanting, and lighting and some of the sensors. So the nutrient system will be by and large be using standard nutrient system technology that we take from industry.
Very good, thanks. Another question that we got in was, with this farming method, do you think it would be easy to eliminate the in season, out of season for certain types of crops?
Yes, it's a short answer.
Yeah.
Yeah, like there's no season here, you know.
Yep.
I've had fresh strawberries in Laramie in wintertime, you know. It's yeah, that's one of the beauties of this. You can just, and then we harvest every single day. We'll seed and harvest all the whole thing, and it'll be the same with strawberries. Strawberries will have a much longer life cycle. So like, whereas leafy green life cycle will be about 3 weeks, a strawberry plant will be in the system for probably 1.5 years in total, but we'll be harvesting many times during that 1.5 years.
Yep. And what kind of volumes then, when you talk about, say, like the new farm that you're building in Compton, servicing that kind of, if we call it that local LA region, not that LA can get local, what kind of volumes would you be putting into the trucks every day?
Well, you can work back from the math, but it's basically it's a annual production approximately 2 million kilograms a year of finished goods, is what would be produced out of a farm of LA capacity.
Wow, pretty impressive. And you made a point there while you were talking. You said it's, you could do this in the Arctic, as long as you've got electricity and water. Are there any other challenges you see? I mean, I'm kind of thinking, I guess maybe, there's a lot of infrastructure in the US, a lot of maybe money in the US. What would be apart from maybe finance, what are the big challenges that you would see bringing this into more developing countries where maybe they might benefit even more from this than maybe than established countries, should we say?
That's an interesting one. There are probably many challenges in different developing countries. So I'm probably good. And I think local infrastructure would be one. You need a lot of power to do this. You need very good power infrastructure. Now, depending on some of those local infrastructure, local environments, maybe maybe in those scenarios we'd have locally sited solar infrastructure or something like that. So I would imagine there's a level of sophistication needed. I mean, right now, all our software runs in the cloud, so reliable internet would be a good thing to have. Of course, that could be changed, but our plan of record is to stay cloud-based. No on-prem software if we can avoid it, so pure cloud. But that would certainly be. There are many other challenges to doing this. I mean, right now, the big focus is on demonstrating unit economics at scale, which is the prerequisite to really go for it in the market, and then to establish the multi-crop platform. Once we have those in place, then we can scale it out. I would imagine we'll be mainly focusing on developed countries initially, or anything with the prerequisites of the kind of infrastructure that we would need. There's a lot of possibilities in like the Middle East and places like that. Probably Ireland too has some good opportunities for us, so things like that.
Very good. I have one last question from Wagner here. He said, are you using any open source software to monitor water and air temperature, or any plans to open source the Plenty OS? That's an interesting question.
So I don't think anybody builds anything without using open source software these days. So I will say, we're heavy users of Amazon cloud services, so they're not necessarily open source, but they're not ours. There's all sorts of libraries that we use. We don't specifically have an open source monitoring system. We've built connection components for specialized devices. We've got our own hookups there, but we do it on an IoT protocol, MQTT, for transportation. And I would say that the single biggest open source that we use that's kind of defined in the architecture is this ACA system for orchestration. So that's a pretty key open source library that we've been using effectively. I would say the other areas of open source that are maybe in the more specialized category would be open source around optimization. And so if anybody's interested in in learning more about optimization, OR tools is a fantastic system for mixed integer linear programming problems and such. And that's another one that we use.
Fantastic. Conor, thank you so much. I appreciate it. I know you're due out the farm and you're taking this, as you said, from a hotel room in Venice Beach. So I'm out today to talk us through this. It's, the theme we've had today is looking at kind of sustainability, and I think what you guys are doing there is right on the money, and it was fantastic, folks. So thank you so much for taking the time to join us today.
My pleasure. Thank you very much, and good to see you again, Seamus.
Yeah, great to catch up again after so many years. Take care. And just for everyone, thank you again for joining. Tomorrow is our last day at the AtlanTec Festival. Again, we'd love to hear your feedback just on today's session with Conor or on any of the sessions that have been on this week's. Using the handle @AtlanTecFest and use the hashtag @AtlanTec. And with that, I'll say thank you to everybody. And again, thanks again, Conor.
My pleasure. Take care, everybody. Bye-bye.